When physicists test the universe, they extract finite strings of data from their instruments, collapsing them into rigid, discrete arrays. A contradiction sits right at the center of modern physical theory. Every experimental record we have ever produced is a finite string of bits. Yet theories we build to explain those bits rely on real-valued continuous parameters and infinite-dimensional mathematics. This gap creates a quiet anxiety. If our raw evidence is strictly discrete, how can we be certain that the continuous models we rely on aren't simply mathematical illusions, constructed to make the math easier? For decades, physicists have looked to pure mathematics for a rescue, specifically to Elaine Kahn's, and a concept known as operator algebraic rigidity. The hope was that a rigorous mathematical theorem could prove that certain discrete algebraic structures lock into exactly one continuous form. If finite records cannot definitively prove a unique continuous symmetry, the foundational models of quantum field theory appear physically indeterminate. A failure of mathematical rigidity would seem to erase the empirical content of gauge theory entirely. This diagram outlines the proposed defense, known as the rigidity necessity thesis. It asserts a strict chain of inference. Finite empirical records yield finite lattice algebras, which lead to a rigid continuum von Neumann algebra, which finally reconstructs a unique continuous gauge group. The entire pipeline relies on this specific step. The assumption is that we must be able to take discrete group factors and have them perfectly inverted back into unique continuous gauge groups. Without this inversion, the argument goes, physical determination is lost. The mathematics holding this pipeline together are typed wrong. It conflates entirely distinct mathematical objects and treats a forward-moving construction process as if it were a reverse engineering tool. To correct this, we have to pull apart the definitions holding it together. We will audit the word discrete, demonstrate the forward-only nature of lattice scaling, and introduce a physical ontology that actually explains how continuous realities cast finite shadows. Defending the laws of physics with broken math is more dangerous than admitting the limits of our models. We have to establish exactly what a finite record actually implies about reality. This grid maps 4 incompatible definitions of discrete. First, empirical, finite experimental data. Second, lattice, countable structures with continuous variables. Third, group. Kahne's addresses countably infinite groups, not compact Lie groups. Fourth, truncation, an artificial cutoff into a finite matrix. You can pull a finite sample from a continuous Gaussian distribution, but that sample doesn't mean the underlying universal law is a rigid step function. The sample is finite. The source geometry is continuous. Lumping these distinct concepts under the blanket term discrete data creates a logical bridge where none exists. The first step of the pipeline fails. This first step of the rigidity pipeline fails by a simple type mismatch. We challenge the assumption that a physical model on a finite lattice naturally yields finite-dimensional operator algebras. Look at the exact kinematics of a single lattice link carrying a compact gauge group. The Peter-Weyl theorem breaks its Hilbert space into irreducible representations. A positive-dimensional compact Lie group has infinitely many, extending the exact space infinitely upward. To force that infinite stack down into a finite matrix, you must introduce a deliberate artificial truncation rule. The moment you execute that cutoff, the bare algebra permanently loses memory of the continuous group. A finite lattice does not equal a finite mathematical ontology. The assumption that finite observables naturally emerge from a compact group lattice is false. Confirming the second step of the rigidity pipeline is a category error. To see how continuous data actually behaves on a lattice, we must deeply look at the process of scaling. Physicists use Wilson lattice gauge theory to study the continuum limit as lattice spacing approaches 0. This timeline charts the process. The compact gauge group must be injected initially to define the Wilson action. Kahn's rigidity attempts a backward shortcut from a terminal algebra, but the continuum limit is a forward construction, not a reverse engineering tool. The physics of the renormalization group guarantees a many-to-one mapping. Irrelevant operators and discretization choices fall away as you scale. This means different microscopic lattices can and will yield the exact same continuum limit. Empirical equivalence does not require source identity. We expect microscopic non-uniqueness. Demanding a perfectly invertible algebraic code from the terminal end of a continuum limit is an arbitrary mathematical constraint that physical theory does not require. If bare operator algebras cannot reconstruct the continuous gauge group, how does algebraic quantum field theory actually accomplish it? The proper route is DHR superselection theory. This web visualizes a symmetric rigid tensor category, plotting localized charges. It recovers the continuous group not from a single isolated factor, but requires this enriched category of subobjects and conjugate statistics to reconstruct the group's exact geometry. Continuous reconstruction is possible. It simply requires a rich, structured family of physical operations. Kahn's rigidity attempts to decode a complex physical ontology using an isolated mathematical invariant that lacks the required data. We can now address the underlying physical ontology. If the universe doesn't rely on perfectly invertible algebraic codes, how does a genuinely continuous reality consistently generate discrete empirical data? The TCGS-SEQUENTION framework supplies a direct geometric answer. Existence is divided between a continuous four-dimensional counterspace, the source, and an operational three-dimensional projection plane, the shadow. The extrinsic constitutive law acts as a projector. It takes the invariant gauge data from the continuous source and renders it into conditional, discrete readouts onto the shadow plane below. The resulting readouts are entirely selector-evaluated. They depend on your measurement framing, the operational time, and boundary conditions. The act of measuring a slice of the shadow does not alter the invariant continuous source above it. A shadow that appears many-to-one or ambiguous on the floor does not erase the solid reality of the object casting it. A non-injective readout is a feature of the projection geometry, not a failure of the source ontology. The rigidity necessity thesis failed by demanding the three-dimensional shadow map perfectly and uniquely back to the four-dimensional source. Mathematically, that inversion is a categorical impossibility. The inability to uniquely invert a discrete group factor means only that this specific invariant is incomplete. It poses zero threat to the standard model, lattice gauge theory, or our understanding of quantum fields. A physical theory is an active, enriched readout of reality. It requires dynamic data, geometry, and observer orientation to function. It is not an unlabeled matrix waiting to be solved. We do not need infinite mathematical rigidity to execute precise empirical science. We just need to stop mistaking the finite shadows registered on our instruments for the continuous limits of the universe.